Thank you for the introduction. I am Miguel Alvarado, CTO at Mindstrong, and today we're going to talk about what your phone data can say about your mental health. So here's the agenda of what we're going to talk about. We're going to talk about who we are, Mindstrong. We're going to talk about how can we passively monitor mental health through a mobile device. We're going to talk about synthetic biomarkers going from typing data to digital phenotyping. And we're going to talk a little bit about what that is. We're going to talk about how these synthetic biomarkers are used and what comes after what we have today, what's coming next. So who are we? We're Mindstrong. Before we get into who Mindstrong is, some statistics to contextualize things. Here's some mental health statistics from 2021. So 19% of adults in 2021 were experiencing mental illness, equivalent to over 47 million Americans. 4.55% are experiencing a severe mental illness. In our opinion, these statistics are actually a little bit lower than they actually are. So this is the original founding hypothesis of Mindstrong. We all carry our smartphones around all day. What if we're leaving a digital signal behind that, if properly decoded, could help a mental health provider provide better care to those patients, prevent a crisis? What if that were possible? We want to make it so. We want to make it possible. We are setting a new standard for mental health care. So what do we do exactly? So we're a clinical company and a tech company. We offer therapy and psychiatry services, but we also build products for our clinical staff and for our members, that is, our patients. We have engineers, we have scientists and clinicians building products together. So this is our Mindstrong care model. This is how we go about care. I'm not going to go into every single one of these things. I'm really going to zoom into the middle one, which is continuous measurement. We continuously measure so that we can actually measure the outcomes of the other side. We want to make sure that we can prove that the patients are getting better over time. And we do it passively and we do it actively. Actively means that we ask the patients for some action, for instance, to fill out surveys so that we can measure things. But there's also passive measurement, which means that we will get data from the mobile device or other devices eventually from the patient, and we will infer things about their mental health and how they're doing. So let's talk a bit about continuous measurement. The status quo today is to give patients questionnaires using tools like DSM and PHQ-9 at some cadence. These are tools used in the world of, that have been used in the world of therapy for some time. But even that kind of continuous measurement is uncommon with most mental health providers. So we want to set a new standard for passive and active measurement at Mindstrong. How can we passively monitor your mental health? Can we know something about your mental state from raw phone data? Can we infer some mental state from typing data? So for instance, being able to measure the dynamics of your keystrokes, would that tell us something about your mental health? The short answer is yes. We collect raw typing data and then we synthesize biomarkers from that data. We capture data on how you type, so the dynamics of your typing, and we synthesize biomarkers from that data. So that for us is the beginning of digital phenotyping. And how do we do it? Very carefully. Well, more specifically, first of all, let's define digital phenotyping to contextualize it. So digital phenotyping is a new science of collecting data from smart devices to build rich, personalized digital pictures of behavior. Then we track markers for depression and anxiety, and those help develop new ways to diagnose illness. And also, this is very important, a way to choose effective treatments and detect relapse before it occurs. So if you think about the last bit there, it really allows us to personalize care for people. So what is a biomarker? So this is the Wikipedia definition of biomarker. So biomarker, short for biological marker, is an objective measure that captures what is happening in a cell or an organism at a given moment. Biomarkers can serve as an early warning system for your health. Contextualizing to Mindstrong, our biomarkers are measuring your cognitive capabilities, or they're attempting to measure your cognitive capabilities. So they're objective measures that are capturing what's going on in your brain. So getting more into the software side of things. So this is very high level, our backend services architecture. So I'm not going to go into all the different services, but this is just to illustrate at a glance what our backend systems look like, right? So we have different services to deal with different things. This powers our provider experience, but also our member experience. Now, this is where it gets a little bit more interesting and specific to what we're talking about. So this is our end-to-end pipeline where we go from the raw phone logs from iOS and Android all the way down to biomarkers. So let me describe this pipeline to you. As I said, we collect raw data in iOS and Android. That data is stored in the device as raw Avro data. We push the Avro data at a cadence to a S3 bucket where we capture all of our raw data. There's an event that gets triggered when new data is received, and there's this Lambda function that extracts metadata and sends the metadata to this metadata service. And the metadata service saves the metadata into a database that we call the pipeline DB. This is the database that's kind of keeping the state needed for this whole pipeline to run. Then we have an hourly job that on an hourly cadence looks at the past full hour that was captured, looks at the metadata, fetches the metadata from the pipeline DB, takes all the Avro data and it turns it into Parquet and stores the Parquet data into another S3 bucket. Now the data is ready to be processed. We turned it into Parquet because it can be analyzed and just processed quicker. So as our data sets grow, this will be more efficient than ever. There's a couple other nuances of why Parquet is convenient. So once the data is there, then there's another job that also at a time cadence, I believe it's every hour as well, it fetches the data from the bucket and it does filtering and scoring of the data. And after that process, the next stage is going to do feature extraction of the data. This is still running within EMR, Elastic MapReduce. These are a couple of different MapReduce jobs inside EMR. The result of that is now like our first kind of rendition of the digital biomarkers. And we have cognitive biomarkers and we have a clinical biomarker. I'll go into explain what those are in a little bit. Now from that S3 bucket, we then send the S3 keys to a message bus, which the message then is received by the prediction service. Then the prediction service, based on the keys that it received, it fetches the actual Parquet files from S3. It does inference against not just one, the diagram has one, it's actually a couple different models. So it does inferences against trained models, and then it takes those scores and then it saves the scores from the inference requests into the pipeline DB. So now we have scored data that then we can do something with. So we have some predictions, in other words, that we can do something with. We send the scores into a message bus, and then now that gets consumed by a biomarker alert and messaging service. So there's many things that we do with the biomarkers, but one of the things is that we predict how you may be doing mentally. So if you're not doing so well, we want to send an alert. So that's the job of this service. So we store state data back in the pipeline DB, and now we push alerts when needed to this message bus for consumers that then are involved to notify the clinicians that there's an emergency and we should look into what the alert is. So in other words, when these alerts go off, it means that somebody is in a critical state and a clinician needs to intervene, they need to do an intervention. The data from the pipeline database can also be fetched by other Mindstrong services that may care about these alerts and just the scoring of the biomarkers. So that's more or less how it works. I mean, there's a lot of detail, but that gives you the high level picture. And I mentioned that there's two types of biomarkers, right? So we have these cognitive biomarkers. These are inferring how you're doing from an executive function perspective, cognitive control, working memory, processing speed, and emotional valence. Those biomarkers are looking at how you're doing with respect to the mean, and they're looking at deviations from the mean, and they're going to visualize those deviations from the mean. Then we have a clinical biomarker, which is predicting your CGI-S score. That score tells us how you're doing from a mental state perspective. A score of 5 to 7 would be critical. Like 7 is like you need to be hospitalized. All this is currently in beta. You know, we're barely starting to scratch the surface of digital phenotyping. So both of these types of biomarkers at the moment have some challenges. They're not perfect by any shape of imagination at the moment, but the objective is to continue to make them better as we start collecting more cognitive data over time. But this is a great starting point. So the biomarkers that we synthesize today are composed by the following. So on the cognitive, first of all, they're both powered by 1,035 features that we calculate from the typing data. We have the cognitive biomarkers, which again, the output of these is the predicted population normalized deviation from mean in each domain. I mentioned all the 5 domains. And the method used is a supervised kernel PCA method for feature selection and dimensionality reduction. And then we feed that into just a simple linear regression model. And the utilization of the output is display. So we show graphs that show you the deviations from the mean, and I'll illustrate that in a moment. The clinical biomarker, the output is CGI severity alert. So a CGI score is typically going from 1 to 7. So again, this is telling us if anybody is, 5 and above, and that's when the alert goes off. The method used is a convolutional neural network that tries to predict 3 different scores. So even though CGI-S goes from 1 to 7, we've kind of bucketed the scores into 3 different scores. So 3 is anything from 5 and above. If we predict 3, that's when the alert goes off. The utilization inside the platform is alerts and then actions. So our clinicians intervene when alerts go off. This is now getting into how the raw data looks like inside the device. So on Android, we collect the data directly from the OS. iOS is a lot more restricted, so we deployed our own keyboard based on a code base called Flexi. We have licensed Flexi from a third-party company, and then we tweaked it a little bit and we put inside our app. So when you install Mindstrong, you have the option to also install our own keyboard. That's how we're able to collect more data about how you're typing. If I go to Athena in AWS and I look at, the table structure of the data that is the raw sensor data, this is more or less what it looks like. These are the columns. So, as you would expect, there's timestamps and a bunch of other things. I'm not going to get into a lot of detail, but just wanted to give you an at-a-glance view of how the raw data looks like, more or less. This is more or less it. This is a Avro to JSON conversion right out of a log, a live log coming from an iOS device. I talked about the 1,035 features. I am not going to go into all the specification of the 1,035 features. We could be here for a couple hours. These are just some examples of what the features are, right? So as you can tell by the names, they tell you something about the dynamics of how you're typing, right? So it tells you like how many times you've done something, like at the speed at which you've done something, how you're scrolling, et cetera, et cetera. Again, this is just to illustrate like what are these features more or less? What does it mean to capture the dynamics of how you're typing? And this is just one category of features. These are the category is pattern-based features. There's others, obviously, but this gives you an idea. So there we go. We got initial phenotyping. We went from raw phone data to biomarkers. So, we're starting with cognitive biomarkers in our phenotyping journey. So these are the graphs that I mentioned before. So these are the graphs of the 5 domains, the 5 cognitive domains. These can be viewed inside our mobile app, but they can also be viewed in the web-based EHR software that we deliver for our clinicians to interact with. So you can see, there's kind of like the dotted line gives you the trend. You see that as the lines get away from the white and get into the darker shades of the color, those are the noticeable deviations from the mean. So you're looking at 1 or 2 standard deviations from the mean. So how are they used? So this is all very cool and interesting, right? But what's the utility of this? So again, this is our humble beginnings in the area of phenotyping. But let's start with, do they work, right? So what is the proof that this actually works, that this is actually telling us something about your cognitive state? So hypothesis to prove that they work. Cognitive functioning, except for negative valence, decreases with age, right? So your executive function, your working memory, etc., they degrade as you get older. And there's a lot of literature, scientific literature that talks about this. So what we wanted to prove is, okay, so if our biomarkers are saying the right things, if we look at different populations based on age, we should see that they decrease with age in the same way that the literature says. So in these graphs, you can see that there's a line. The line is what the literature says in terms of like how these domains decrease as age gets higher. So you can see, you see the lines going further down as time goes by, right? And then what we did is we plotted data coming from our biomarkers on top of those lines. So the scatter plots that you see there are coming from our biomarkers, but if you see the shape of those plots, you can see that they're going down at the same velocity, if you will, as the lines coming from the literature. We did some regression analysis that then confirmed that the hypothesis is correct, right? So the cognitive functioning decreases with age. In this case, beta equals to negative 0.018. Interpretation: with every 10 years older, as you get older every 10 years, cognitive functioning decreases 0.18. There's the typo there. That should be disease, that should be decreased. So how are they used? So this is pretty interesting. It's cool that they work, but how are they used? Well, on one side, as part of our measurement-based care model, is something that clinicians observe over time. On the CGIS, this is, I think, where we have the most utility right now. There's interventions that get done when the alerts go off. Clinicians reach out to patients. At the state that we're in, there are false positives. And there's room for error there. And what we've learned, which is an important learning, is that our patients prefer us to reach out to them, even if it's a false positive. We prefer as well because we can make sure that we're not missing a potentially critical incident. The other way that they're used is for research, internal and external. We have partnered with various research labs, and they've done research on our platform. Various labs coming from Stanford, a few other universities. This list of like maybe 7 or 8 different research partners that have found utility in this data. So what I've mentioned really is just the early building blocks for future capabilities. Again, we're just getting started with all this. So what's next? So we're just going to get more data from the app. There's things that patients can do inside the app. They can message the therapist. There's some people have done in-app text message therapy sessions. So we want to exploit that. We want to use the text transcripts from the Zoom sessions. We want to use the audio from audio journaling in sessions. We don't have audio journaling yet. That's a feature at some point in the roadmap. We want to leverage audio as well. And we want to get data from things like cognitive games. So cognitive games can sometimes give us a proof that there's something wrong with the patient. In other words, we have a signal saying, hey, that there may be a problem with how somebody's feeling, but there may be a false positive. So how do you confirm that it's not a false positive? You may deploy a quick cognitive game that somebody can play in a few seconds that then gives us additional cognitive data to then prove that it's true or not. That data, as you can imagine, can then be used for further training data for other models. So clinicians and technology will set a new standard for mental health, combining, the expertise of human clinicians and combining the expertise of technologists to build capabilities. It will set a new standard for mental health. We're combining the power of clinicians, data, and AI. That's all I have for now. Thank you very much. Thank you for your time. I will stay a little bit longer for Q&A. If you have any questions about biomarkers, data, infrastructure, software, whatever you have questions about. Thank you very much for listening.